Now we'll start the next topic, that is types of recursions. So here are the list of types of recursions. I'll be discussing each of them one by taking some examples. See, the tail recursion is the first one, then head recursion, tree recursion, indirect recursion, and nested recursion. So we'll look at them one by one. Let us start with tail recursion. Yeah, here is the first recursion, that is tail recursion. We have already seen this type of recursion. This function already I have explained in the previous video. Now it is a tail recursion. So what does it mean by tail recursion? If a recursive function is calling itself, and that recursive call, this is called as recursive call, and that call is the last statement in a function, then it is called as tail recursion. After that call, there is nothing. It is not performing anything. So it is called as tail recursion. For example, this is fun and taking some parameter n, and if n is greater than 0, the similar one I am writing, and there are some statements inside, then the last thing is it is calling itself by a reduced value of n. See, what all it has to do, it is performing first, then it is calling itself. So in this example, I have just written printf, but there may be a lot of things a function may be doing. All those things it has finished, then it is making a call to itself. So if it's a last statement, then it is called as tail recursion. So this means that all these operations will be performed at calling time only, and the function will not be performing any operation at returning time. Everything is performed at calling time only. So that's why it is tail recursion. Now suppose there is something written here, plus n, means along with the function call some operation is done. Then if this is the case, then when this operation will be performed, this will be performed at return time, because unless the result of this function is known, addition cannot be done. The value of the function is added with n, so this addition can be performed only at returning time. So in this function there is something remaining that has to be performed at returning time, so it cannot be a tail recursion. Tail recursion means at returning time it doesn't have to perform anything at all. So this is a perfect example of tail recursion, or else if I remove any processing here, then it is a tail recursion. Now next I will compare tail recursion with loops. Now comparison of tail recursion with a loop. So first and the foremost thing I have to tell you is that every recursive function can be written as a loop, or vice versa. Every loop can also be converted in the form of a recursion. But now let us compare tail recursion with loop. See, this is a tail recursion. Already you know the answer in the previous video. Already I have traced this one and shown the output. If we call this function by passing 3, so it will print 3, 2, 1. And it will stop when the value of n becomes 0. So it will print the values 3, 2, 1, and it will print in calling phase. Now same function, I want to write it using loop instead of recursion. So I will write on the function here void fun, which it takes parameter n, and the first thing is n greater than 0. I will write n greater than 0. But instead of if, I will write it as while. Then inside this printf statement, this is printf percentile d and some space n. Then calling function again itself by reduced value of n. So let us do n minus minus. That's it. So if I call this function by passing value 3, then 3 will be passed here, then it will first print 3, then it will make 2, and again repeat. So print 2, then repeat, print 1, then repeat, it is 0, so it will stop. So this will work same as that recursion. As it is, I have converted, just instead of conditional statement, I made it as a loop. Instead of conditional statement, I made it as a loop, and instead of function call with reduced value of n, decreased value of n, I have just written n minus minus. So the function is same as that one. Output is same, and the structure also, if you see, it looks more similar. That's what. So the point that I have to tell here is that tail recursions can be easily converted in the form of a loop. Now let us decide who is efficient. In terms of time, if you analyze, this is printing 3 values and this will also print 3 values. So the amount of time spent is same. Whatever the value of n is given, if it is 3, then it is 3. If it is 5, then it is 5. So it means the time taken by both of them is order of n. So time is same. So the time taken by both of them is same. So the time is order of n. But let us analyze the space. This is a recursive function. It internally utilizes stack. So for the value of a 3, it will create a total 4 activation records in a stack. This already we have done the analysis. So for n, the space taken by this one is order of n. But what about this one? This is a loop function. So how many activation records will be created? Only one. It is not calling itself again. So the space complexity for this one is order of 1. So it will just create only one activation record. So that is constant. So we say it is 1, order of 1. That is constant. So there it is order of n and here it is order of 1. So the conclusion is, if you have to write a tail recursion, then better you convert it into a loop that is more efficient in terms of space. But this will not be true for every type of recursion or loop. In case of tail recursion, loop is efficient. And even I have to tell one more point, that some compilers under code optimization inside compiler, they will check if you have written any function which is a tail recursion, then they will try to convert it in the form of a loop. It means they will try to reduce the space consumption and they will utilize only order of 1 space. So your function will be converted into object code just like a loop where the space is reduced. So that's all about tail recursion. Now next we will see head recursion.